Hi guys, so in this lecture we'll be starting off with geometrical isomerism. Hope you remember that we divided the class of isomerism into structural and stereo, and under stereo also we divided into um, configurational and conformational. So under configurational we'll be we actually subdivided into geometrical and optical. So we'll be seeing the geometrical part of our stereo isomerism. Okay. So let's get started. Geometrical isomerism. Okay, so what is geometrical isomerism? Isomerism due to change in geometry is geometrical isomerism. Simple definition. Isomerism due to change in geometry is called geometrical isomerism. Okay, so let me list down the following compounds which can show geometrical isomerism. Following compounds can show geometrical isomerism. Okay, so first is compound containing double bond between different atoms, cyclic alkanes or cyclic alkenes. Third is cumulines. Okay, let me write it again. Cumuline. Fourth is bicyclo. Fifth is enol, and sixth is enolate ions. We'll be talking about enol and enolate ions in a short while, but before, let us start with the conditions required for compounds to be in geometrical isomerism. Conditions for geometrical isomerism. So the conditions are: A, they have to be stereoisomer first. So we'll talk about what is known as stereoisomer. B, they have to be means the across the bond rotation has to be restricted rotation restricted. And third point is there should be some change in the areal distance of the substituents or group attached to the compounds which are exhibiting geometrical isomerism. So different areal distances. So we will talk about what is the implication of all these things and what do I exactly mean when I say all those conditions. So let us take this with the help of an example. If we have this double bond, then you can see that the areal distance. Okay, let me make the second example also first, the geometrical isomer counterpart of it. So we have something like this was the areal distance L1 in first compound, and this is L2 in the second compound. So L2 is greater than L1, so there is a difference in areal distance. I called it delta areal. Difference in areal distance. Okay, so there is a difference in areal distance, so it actually qualifies for being in geometrical isomerism. And why is rotational restricted? Because it is a double bond. Okay, so let us take second example wherein we need to compare between these two, whether these two are in geometrical isomerism or not. So as you can see that there is a sigma bond between this carbon atom and this carbon atom, hence rotation is not restricted, and if the rotation is not restricted, it is not qualifying for conditions, the B condition for compounds to be in geometrical isomerism. Okay, and they are called conformers and not uh, not in geometrical isomerism. Let us take at another example. Look at another example. We have here F I double bond F and Br, and what is the counterpart or geometrical isomer for it is Br. Pardon, Br, F and I. So here you can see that the most bulky, for the bulky group, the aerial distance is changing. For the bulky group, this was the bulky group. So the aerial distance here was L1 and the aerial distance here is L2. Hence there is a difference in aerial distance is there. Hence these are in geometrical isomerism. And one more thing, when we need to compare, there is a naming convention for geometrical isomerism as well. So this compound is called Z and this is called E. The configuration is Z and it is E configured. What do I mean is, if the most bulky groups are opposite to each other or at a more distance to each other, then it is called E configuration. For L2 greater than L1, so this will be E, and for L1 this would be when the most bulky groups are nearer to each other. So for L1 we have Z, for L2 we have E. Okay, so this can also be seen as, we have some more example. We have this one, and so here more bulky groups are I and Cl. So in this case it would be E, Z, and here it would be E. Why? More bulky groups are on opposite side, more bulky groups on same side. Okay, now let me write down some of the more definitions and some documentation about stereoisomerism. So as I explained in the earlier definition, let me write the summary of this is stereoisomerism or stereoisomers, which has restricted rotation and different aerial distance are known as geometrical isomers. Okay, and geometrical isomers has different physical and chemical properties, and if there is a presence of two like groups on the same carbon of alkane, then it will not show geometrical isomerism. So let me write this also. So geometrical isomers have different physical and chemical properties, and if there is okay, let me write down a separate point because it is very important. So if there is a presence of two like groups on same carbon of alkene, then it will not show geometrical isomerism. Geometrical isomerism. Okay, so what are actually conformers? So let me write down about conformers. So conformers are stereoisomers which are formed by rotation across sigma bond. So these are stereoisomers which are formed by rotation across sigma bond. Okay, and one more point in the geometrical isomerism is that alkynes will not show geometrical isomerism because areal distance cannot be measured if we have only one substituent attached to each carbon atom in alkyne, in the case of alkyne. Hence alkynes will not show geometrical isomerism because there is no concept of areal distance among two heavy bulky groups in alkynes. Okay, so obviously do we always need to have a carbon atom in in the case of geometrical isomerism for it to show geometrical isomerism? No. So minimum carbon, if the question is asked of this form, is that minimum carbon needed by any compound to show geometrical isomerism, by any compound to show geometrical isomerism, the answer should be 0 because we just looked at n double bond and can also be in geometrical isomerism. So what is the minimum carbon needed by alkene to show geometrical isomerism? So the minimum carbon needed by alkene to show geometrical isomerism would be how many? Just 2, right? But when I say that the minimum carbon needed by alkene to show geometrical isomerism, provided there is no functional group attached or we can use it, then the answer would be 4, right? So minimum carbons, we are talking about just carbons which we need. We are not talking about, you are not provided with any halogens, any other substituents or anything like that. So the minimum carbons needed by any compound to show geometrical isomerism would be 4. Okay, so with this we end our lecture, and in the next lecture we'll be seeing cyclic geometrical isomerism in case of cyclic compounds, and we'll understand the concept of cumulines. Okay, so till then, good luck and goodbye.